Today's talk is Professor Haridas. Haridas, I don't think he requires introduction, but still, I request the organizer of the meeting, Professor Sayanthan, to properly introduce him, actually, to those who are actually quite young in this audience, actually.
Thank you.
Thanks, Professor Ravindran. And as you know, Professor Haridas has been giving a series of lectures this week also. So you must have already met him, and our senior colleagues already know him. So I don't need to introduce him formally. But for the students, I just wanted to tell you that he was one of the founding fathers of lattice gauge theory initiative in IMSC, and a lot of nice fundamental works were done at our institute, and also our inbuilt supercomputer Cabru that was built in 2004. That was actually the fastest supercomputer during that time, which was used for doing scientific calculations. So this was a great achievement for our institute, and it was mainly his initiative with which we could gain an excellence in supercomputing and using supercomputers to do basic sciences. So that was one of the things among many which he contributed significantly. So please, Professor Haridas, I would not take much time and request you to kindly give your talk. Thanks.
Well, thank you very much. As always, it gives me great pleasure to be back here, an institution where I spent the longest number of years in my long academic career. So it's a special place for me. And I'm touched by the gesture of the director and the institute in listing my talk in your highbrow series. And I hope I can do justice to that. One of the reasons why I came to Chennai was that I'm in the process of writing a book, and I thought that I come here and I'll shut myself up in a room and go to library when nobody goes there, and I'll speed up the writing of this book. You always propose and something else happens to it. Book is progressed, but not as much as I had hoped it would. And the three lectures I'm giving to the students mainly, and this, are in some sense the dry run of my book, because this book covers a very wide landscape of developments in physics. And what struck me was how the notion of dispersion relations, has a footprint at almost every stage. So I thought that I would convey this connectedness of the dispersion relations, because it started in classical optics long ago. There is a certain confusion in terminology. There are relations which tell how things like refractive index and absorption coefficient depend on frequency. And they are also called sometimes dispersion relations. That's a misnomer. In a sense, they are not completely wrong, but what they are describing is the color dependence of certain quantities. But the dispersion relations, in the sense I'm going to talk about today, is something quite different. Okay. So dispersion, as you might have roughly guessed, has to do with color, and I thought I'll make a point of that by putting the dispersion in a different color, but somehow it's not coming out right, and that's partly the Beamer's problem. So, if I have to sum up the theme of my talk today, it would be something like, it's a complex world. you will say, big deal. We all know it's a complex world. But here we will see that it's a complex world in a very specific way. I went to United States to do my PhD in 1967. And this complex world haunted me as a graduate student. And in fact, at that time, this book by Eden, Lanchoff, Olive, and Polkinghorne, called The Analytic Asymmetrics, it's a beautiful book, was considered the Bible for particle physics on the West Coast. Okay? The West Coast and East Coast in the United States at that time, they pursued very different traditions. And in the West Coast, it was all asymmetric theory, etc., etc. And I will tell you more about that. So this sentence said, one of the most important discoveries in elementary particle physics has been that of the complex angular momentum plane. Nothing could have disheartened me more than this statement, because I thought I'm going to this land of big science to learn about elementary particles, field theory, what have you, and I'm told that complex J-plane is what you should be mastering. Okay. And the prevailing atmosphere was also like that. A lot of very complicated calculations with contours and, how to slip from one Riemann sheet to the other, etc. And I lost interest in research, more or less, because of this wild goose chase on the complex plane. But today, unfortunately, this always happens in life, that understanding comes when it's somewhat too late. Okay. Now I see that was the period where some wonderful developments took place. It was really a revolution of sorts. And that is what I would like to convey to you, so that what I lost out as a graduate student need not be the misery of everybody. So that's the overall motivation, but let me start this talk with a poser. Why do we see the visible part of the electromagnetic spectrum? That looks like a, oxymoron, obvious. It's visible because that is what it's visible. Okay, that's not what I mean. This is a very anthropomorphic term. It means visible to the humans. And in terms of the electromagnetic spectrum, it's a tiny, tiny window. So it's really a wonder, a miracle that, we see in this very, very narrow range of the electromagnetic spectrum. Now they say chickens can see in the infrared, now I can understand why they don't want to go near a tandoor, okay? And maybe donkeys can see in the ultraviolet, etc. But predominantly the living beings see in this narrow window. Just keep it in the back of your mind. So what is dispersion? Dispersion is any phenomena that depends on color, colloquially speaking. And as a physicist, we shouldn't be talking colloquially. It means anything that depends on wavelength, frequency, etc. And so here is a very classic demonstration which Newton is supposed to have performed, where you take a prism, and I've deliberately shown it in the opposite way that you normally see this. You send white light, and then it breaks up into various colors. The reverse is more fun and not easy to do, but it's also possible. Now, whether Newton did this experiment or not, we don't know. Physics is full of folklores. They also say he discovered gravity because Apple fell on it. And now some of our nationalist-minded people might want to claim that apple actually was taken from Jesuits from Himachal Pradesh to, Oxford. So did apple really follow Newton? We don't care. It doesn't matter. In fact, according to my friend Vishweshwara, that is not how gravity was discovered. It was actually discovered in Kerala, where a coconut fell on the head of a Nambudiri, and unfortunately, he perished before he published. Most of us publish after we perish. Most of us perish after we publish, but he perished before published. So these are all stories. Important point is, white light was seen to be made up of different colors. So what's the basis of this prism phenomena? And that has to do with the notion of refractive index. We have all done this experiment so many times. Okay? In fact, I learned about it when I grew up in a small village, and in the village we don't have this RCC roofs, we have tiles, and tiles break and there are little holes, and sunlight comes, and usually in those days water used to be collected in a tank, and when the sunlight falls onto the water, you could see its path and it bends. A friend of mine showed it to me. It was striking. Okay. So that is refraction, and when refraction depends on color, you get that prism phenomenon. In fact, if you keep your eyes open, you don't have to go to a lab, you don't need prisms, you can see it everywhere. On a rainy day, if you're wearing glasses, a drop of water falls on it, and you can see this. Or you have long eyelashes, then the drop falls on your eyelash, and you can see this. And there are many manifestations of it. Some of them are very beautiful and striking. If you're flying, once in a while, if you're lucky, you can catch the shadow of the plane, as in this picture here, and surrounding it you see a full rainbow, and these are called circular rainbows, and then there are double rainbows, etc., etc., etc. And there's folklore that at the end of the rainbow there is a pot of gold, but actually the pot of gold is the rainbow itself, because it's so beautiful, spectacular. Artists can even do better. They can bring out the vibrancy of color, and there are many, many famous artists. This is by Renoir, the French Impressionist painter, Van Gogh, our own, many painters. The way they have brought out the richness of color is all something which, nature has given to us. Now there is another way you can produce color, and this is called color by absorption. And here is a glass of what is called ale, India Pale Ale. And you see that, at least to me that color is very beautiful, okay? You see a beautiful color coming from absorption. Now you see why pedagogy doesn't always work, because our teachers never sat down with us and gave us a bottle of pale ale to teach us about colors, okay? They should have done that. So here is, now I have refractive index, color dependence of refractive index, and color due to absorption, okay? Now let's see how air absorbs. So that is the absorption coefficient of air, and you see that in the visible window, a narrow window, the absorption coefficient of air drops dramatically, which means that air is almost transparent to the visible light. Of course, that's not the only place. There are other regions, there is radio waves. So in principle, we could be seeing in radios, and that would have been great fun, because you'd be watching the world and also listening to your favorite music, but we don't. we are insensitive to radios. Okay? So what are the various factors that are involved here? Of course, where does the light come from? It comes from the sun. So if in the sun some component of color is not there, then you won't see it. Therefore, we should see the solar spectrum, and visible is not the one that dominates the solar spectrum, but still a good part of the solar spectrum is actually made out of the visible window. So if you put these things together, you start getting some picture. But here is one of the most striking pictures, graphs. Jackson, I don't know how many of you still use Jackson for your electricity magnetism. It's on the whole page. And first time I saw it, I was transfixed by it. This is the absorption coefficient of water. Okay? And what you see is something remarkable. So that's the visible part. A dramatic fall in absorption coefficient by several orders of magnitude. 8 to 9 orders of magnitude, the absorption coefficient for electromagnetic radiation drops around the visible. So undersea life, they would have no problem seeing the visible light. Of course, you must factor in the thickness of the water column. So this is something really, really remarkable. Water is really very special. If you look at the thermal properties, optical properties, it should really be called a divine liquid, even if you're an atheist. I'm neither an atheist nor a religious person nor an agnosticist. Somehow the thought of God never entered my head so far, and now I don't know. Some people say that, in your old age you start thinking of God as some kind of an insurance, okay? But knowing how insurance works, I don't think I'm going to do that. So this is the absorption coefficient of water. So my thesis is that evolution has chosen visible light because, probably everything started in the sea, and water didn't cut off the sunlight. Now this is just for your amusement. Now we ask a question. Are absorption and refractive index related? A priori it looks like there is no relationship between them. Okay? And these concepts developed long before we even started taking the atomic theory seriously. Something happened, media was modeled in some complicated way. Of course, in some very broad sense, everything is related. But that is Deepak Chopra's way of looking at things. Everything is related to everything. This is what I would call unbridled holism. Okay? And such thinking is full of holes. Not that I have anything against holes, if it's a dosa, but if it is thinking, then that kind of holism doesn't lead you anywhere. Okay? So if you leave that kind of thinking out, you have to be more specific. If you say absorption and refractive index are related, how exactly are they related? A priori, first of all, it's not clear they're related, and it's not even clear that relationship is a simple one. Okay? It can be very simple or it could be very complicated. Surprisingly, this question was answered rather late in the day. And here is Kronig. Okay? He and a Dutchman called Kramers answered this question. And the relationship between refractive index and absorption is what I refer to as dispersion relation in this talk. And it's mathematically of a very, very special type. And I'll come to that in a moment. Ralph Koenig came across this while he was studying X-rays. And he wrote a paper, quite a beautiful paper, where he wrote down this relationship. And I'll show you the relationship shortly. And this is what mathematicians would call a Hilbert transform. Okay? There is a Hilbert transform of refractive index gives you absorption coefficient. Hilbert transform of absorption coefficient gives you refractive index. Koenig was the first. I don't know how much of history you guys know. Koenig was also the first one to propose electron spin when he saw anomalous Zeeman effect and all that. And he said, yeah, here is a way of explaining it. And he thought of electron spin. He was a young man, somewhat shy. And he went to visit Pauli, and Pauli destroyed him, said that some very strong words were used. And Koenig thought that, okay, if Pauli is against it, there is no point pursuing it. And he retracted it. Much later, Gaudsmit and Uhlenbeck came with exactly the same idea. Even some calculational mistakes were the same, what Koenig did. And today we remember electron spin by the name of Uhlenbeck and Gaudsmit, whereas Koenig was really the first one to have thought about it. Now let's come to Kramers, Hans Kramers. There is a picture of Kramers with Margarete Bohr, Niels Bohr's wife, and there is that kid is our Bohr. Now none of them is alive. And when I was in Niels Bohr Institute, I got to know both Margarete and our Bohr very well. Okay, so it's kind of a historically cute picture. And the third man is Hans Kramers. And he played a very major role in the development of quantum mechanics. The initial efforts were to understand the color dependence of refractive index. Okay? So that was a dispersion formula. Classically, this was well known, called Drude's formula and so on. And quantum mechanics was in the stage of being formed, and nothing was clear about how quantum mechanics works or how its rules should be interpreted. And so Bohr, Heisenberg, Kramers, Slater, all these guys, they worked on every possible phenomena. Bohr didn't believe in photons at that time, and he wanted to have a theory which did not involve photons, and he inducted Kramers and Slater to do this, which led to a lot of controversy. But that is where the dispersion related thoughts were occupying Kramers' mind. But for us, important point is that independently of Koenig, Kramers also proposed the same formula, same Hilbert transform, but there's a third point. Kramers immediately realized that this Hilbert transform relation is because of causality. Very deep connection he made, simple analysis. Koenig was not aware of this. He just wrote down the dispersion relation, but didn't make the connection to causality. And Kramers was the first one. Today in our country we have an acrimonious debate about language. But as far as language is concerned, Kramers is my hero because he was Dutch. This dispersion relations work was one of the most important works he did. And he goes and publishes it in some obscure conference in Italy. And he writes the paper in French. Okay, so that was the kind of attitude that he had about languages. Now, to track this paper, because I believe in reading originals, because a lot of it can get lost in translation. Okay? So when I'm writing a book, I want to know what the original author said. So I wanted to get hold of this book, this paper, that proceedings is not to be found anywhere. So I thought maybe the Kramer's collection in Leiden would help me. So I wrote to them. They said, first you have to search for that, and then they searched for it. They said, yeah, but we can't issue it to you because you are not a member of our library. If you make a request to X, Y, Z, they may give you this paper. But a week later, I was very surprised to get an email from them with the paper. They said, since you have such an important need for this, we are actually letting you have it, even though our strict rules would have required all that procedure. So I've had help from many librarians while writing books, Niels Bohr Institute. And our own Pandian has been an absolutely indispensable source of support for me. And I would like to thank Pandians and the whole tribe of librarians, because there was a certain kind of dedication which we don't actually acknowledge openly, but it's a very important factor in sustaining our scientific activities. So the paper was called La diffusion de la lumière par les atomes, means the diffusion of light through atoms. So that was the paper. So what is the relationship? What is the relationship with both Kramers and Kronig wrote? And today this is called the Kramers-Kronig dispersion relation. Okay? N is refractive index, and kappa is the absorption, and that's the relationship that you have. It's a linear relationship. It's integral, but it's linear. So in some sense, it's a simple relationship. Okay? And kappa has more or less the same relationship to refractive index. Now, what do these two relationships mean? For that, in the world of physics, everything is real. Okay? When I went to Delhi University, we had a teacher called Manimai Chakravarti. He was a purist. He says, everything is real in physics. I don't want any complex numbers in my class. And he would write down, he taught us electricity, magnets. He taught, write down all the things, real part, imaginary part. He also didn't believe in vectors. He thought these are all fancy mathematics. So he wrote everything in component form, real, imaginary. So he would say, everything in physics has to be real. In poetry, it can be imaginary. Okay? But today we don't think that way. Good that we don't think that way. So what you do is, you take our real refractive index, real absorption coefficient, as a function of frequency, which is also real, and make a complex number out of that. Anybody can do this. You can put any two real numbers, make a complex number. You can put Sonia Gandhi and Mahatma Gandhi and make a complex number, and I'll let you figure out which is the real part and which is the imaginary part. Now that's nothing. Everybody can do it. The next statement is not at all obvious. That now you make the frequency also complex. Okay? Then those two relations are equivalent to saying that the complex permittivity is an analytic function in the upper half complex plan. That's a non-trivial statement. And when you have analytic functions, you can use your Cauchy residue theorem. You apply the Cauchy residue theorem to this object, take the real and imaginary part, and you get that. So, but why is this object an analytic function? Analytic function is something looks like a mathematician's construct. What is it doing in physics? Sometimes some mathematical techniques may help you, but why should physics quantity have this analyticity property? Okay? Now it turns out that Kramers answered this question. And the answer is also quite amazing. Let's look at this a little bit more carefully. First, let's look at a medium, Maxwell's equations in a medium. Okay? If you do Maxwell's equations in vacuum, there is the electric field, magnetic field, currents, finished. You do Maxwell's equations in a medium, there is the E field and the B field, then you have the H field and the D field, and it's all very confusing. You know, except for electrical engineers, most physicists today don't even know what is what. It's very important. Because when you go do superconductivity, if you mix up H and B fields, you're going to get completely wrong. As our professors in Delhi University would say, आपका फंडा बिल्कुल खराब है, you know. So don't mix up E and D, B and H. Now, if you have, first let's take a medium that is non-dispersive, meaning there the refractive index does not depend on color. In such a medium, the D field is proportional to the E field by what is called this permittivity. But in almost every medium, this permittivity is frequency dependent. So when frequency dependent, what do? You better to look at the Fourier transform, and then the D, omega Fourier transform of D is proportional to omega Fourier transform of E through a frequency dependent epsilon. You recognize some convolution here. Fourier coefficients are multiplying, which means in time domain there will be something like a convolution. And that's what happens. D of x of t is E t minus tau times some function g, and that g is related to your permittivity through this relationship. But now, before the external electric field is applied, you cannot have any displacement field. Therefore, for tau negative, G must vanish. This is causality. That mother cannot be younger than the daughter. Okay? Causality. Mothers can look younger than daughters. There is no issue about that. But they can't be born before their daughters. And the various paradoxes, like you take a time machine and you go kill your grandfather, etc., etc. I've never heard of a version where you go kill your siblings. So this shows that siblings are not important in life, okay? But grandfathers are, okay? So this is causality. Cause must come before effect. You can get into some philosophical mess if you talk to philosophers about it, but that's the price that you will have to pay for it. So G of tau has to be 0 for tau less than 0. Now let's invert this. Epsilon omega Now the integral only goes over positive tau, even though we started this for real omega, the omega dependence is manifest. So I can immediately analytically continue this to complex frequencies. And when I do that, in the upper half plane, that means where imaginary part of omega is positive, that epsilon omega doesn't blow up. So epsilon is regular in the upper half plane. So that is the reason why epsilon is an analytic function. And once you have an analytic function, you can just do your Cauchy, residue theorem stuff. And okay, so this is the connection which Kramers made. Kronig did not make this connection. That the analyticity is really due to causality. Okay? Now we come to a period that could be called a crisis in particle physics. Heisenberg was getting increasingly disillusioned with field theory because there are infinity problems and the methods that worked for electrodynamics would not work for meson theories and so on. And by the way, as I said in my class, relativistic quantum field theory was founded by Pauli and Heisenberg. It's an old paper, beautiful. What you call canonical quantization was all worked out in that paper. So he wanted to know, all this field, is just a construct. Can I do away without it? Can I only focus on what is observable and see if all these contradictions that are arising can be avoided? And that was Heisenberg's thinking. And in fact, that's a gold foil collision. And you see they're all particles, and you take any picture from LHC or CDF or whatever, you only see particle tracks. So that was Heisenberg's idea, that what we observe are only the interactions among particles, and can we have a description of physics which will only talk about them and nothing else. And this was his S-matrix program. And he wanted it to be minimalist in the sense that it should obey special relativity, should have relativistic invariance, and probability should be conserved, etc. So these are the minimal ingredients he wanted to put to construct such a theory. Pauli was actually a fair man. He didn't knock down only Kronig because he was a young graduate student. He knocked everybody. He actually told Heisenberg also many rude things. And he told him that, look, your program is just a lot of words and nothing is going to come out of it because it's too general, too vague, and he has written it all down. Okay, you can read these things. In a short letter to editor, Kronig suggested that Heisenberg should expand the basic principles to include causality, because he believed that whatever description that we choose for physics, again, it is just a hunch, no proof, that causality is probably still going to be a good principle. And therefore, he told Heisenberg that in your S-matrix program, you should include causality. But how do you include causality? Through the connection to analyticity. So he said, include analyticity also as a requirement for your S-matrix theory. And the rest, as they say, is history, because it's a very short paper in which Kronig made this suggestion, but it had a deep impact. And let's go on. So this became the starting point for the analytic S-matrix theory, which is the environment I faced when I went as a graduate student. And this was strongly promoted by Jeffrey Chew. My friend Mike Green, by the way, we became friends because we were in a summer school once. And he used to jokingly call it the Jewish physics. You know, you heard of Jewish physics, but this is Jewish physics because Jeffrey Chew. Mike Green went on to become one of the creators of string theory. Even though Chew, he was like a priest, high priest. A lot of the hard work was actually done by Stanley Mandelstam. In Peter Goddard has a very funny way of saying that Chew was almost evangelical in his approach and belief in asymmetric theory. Mandelstam, even though he contributed real stuff, was, according to Peter Goddard, displayed a healthy agnosticism to choose evangelism anywhere. It's a long story. It's very technical. When my book comes, I hope some of you will take a look at it, that the historical, logical, and technical details can be found in my forthcoming book. Then that will be called From Strings to Strings. Okay. So Cronen's idea was to use causality. But what is causality in relativistic field theory? That is actually what is called microcausality. So here is the space-time diagram. So there is the origin there, and these points are space-like, these points are space-like, those are time-like, and along the lines is light-like. We live in four-dimensional world. This is 1 plus 1 dimension, so you have to rotate it in the additional 2 directions, whichever way you want to do it, I don't know. So you actually get cones of space-like regions, which is quite extensive, and the causality has to be equivalent to the principle that no light signal should be exchangeable between space-like points. Chew wanted to banish quantum field theory forever. So that was the atmosphere when I went to California. Field theory was a dirty word. Okay? But Mandelstam was not like that. He used quantum field theory, made some very beautiful calculations, tough calculations of quantum field theory to understand exactly how this analyticity program should be built. He was discovering properties of Feynman graphs, scattering amplitudes in field theory, and from that abstract some general principles for the asymmetric theory. So the first issue was to understand how causality manifests, and this is called principle of microcausality. Okay? Causality requires that a measurement of field at one point should have no influence on field at another point, and fields are operators. That means that if they are at space-like points, you should be able to diagonalize them simultaneously, or they must commute. Okay? So this is the principle of microcausality. Fine, what are you going to do with this? Then came a series of very important works done by Lehmann, Simanzik, and Zimmermann. It's called LSZ. California those days, the closest word to LSZ was LSD. And so if you were telling somebody that, look, hey man, what are you doing? I'm working on LSZ for man. Oh, you mean LSD helps you in physics? Like that. Okay. This is a very, very powerful, non-perturbative way of doing field theory. And they came up with, this went off too fast. In Russia, Bogolubov and others, Haag, many participated in this. I will just show you what kind of amplitude you get from this non-perturbative approach. Don't take it very seriously, just look at some broad features about it. And the amplitude, for example, for alpha with momentum p, beta with momentum q, to p prime, q prime, looks like this. It is also a Fourier transform. And the integrand vanishes when x and y are space-like separated. So it actually looks very similar to what you had in optics. So let's look at that. Amplitude is again Fourier transform, but it's a 4-dimensional Fourier transform. Integrand vanishes over a big region where x, y are space-like separated. In the optics case, time ran along a line, and the half line, which is t less than 0, that g function vanished. The analog of this here is that 1-dimensional line has to be replaced by 4-dimensional manifold, and the region of vanishing of the integrand is this entire space-like, in a region where x and y are space-like. So it's a much more involved situation. Due to Lorentz invariance, analyticity cannot be in individual components. They have to be in terms of invariants. And Mendelssohn was also the one who introduced these invariants, STU. S quantifies the energy of scattering, and T and U quantify scattering angle. And so any analyticity will now have to be realized in terms of these invariants, STU. Okay? So the program is clear, and it had many close parallels to the Kramers program, but technically it was a much, much harder problem. Okay. Now a very important technical breakthrough came at this point, called the integral representation. That scattering amplitude that I wrote down there, mostly Yost and Lehmann and then Dyson showed it satisfies an integral representation. You can write it as in a certain integral form. And this is not assuming any details about interactions, Lagrangians, what have you. It's a very general property of this program. In fact, first it was done by Yost and Lehmann, then it was extended by Dyson. Yost and Lehmann did it for equal mass, and Dyson extended it to unequal mass, and that Dyson's extension was non-trivial. Okay? The punchline was that the integral representation isolated the scattering angle dependence explicitly. Just as in the optics example, the frequency dependence was isolated manifestly. So you could do an analytic continuation on that. And so here, scattering angles could be analytically continued. You could continue scattering angle to imaginary angles. Now, I don't know how many of you realize that all the trigonometric relations we use hold good even when the angles are complex. Just check it. Okay? So now, what Lehmann did was he could analytically continue from real scattering angles to complex scattering angles. And so let us take the cosine of a complex angle, elementary relation, and then you find that this also becomes complex, and it's elementary to check that the real part divided by cos square plus imaginary divided by sin square. This is an ellipse. So what Lehmann did was to enlarge the analyticity from the real line, -1 to +1, to an entire ellipse. and its foci are plus minus 1. And what is more, he gave an expression for the imaginary part of the angle as a function of energy. For imaginary part of the amplitude, that imaginary angle is twice as much. I must speed up a little bit. Now the Lehmann ellipse becomes a stepping stone for proving dispersion relations in relativistic quantum field theory. Path is still very, very tortuous. Okay? In fact, you have to introduce analyticity in masses, etc. Okay? And after a lot of hard work, the so-called fixed T dispersion relations could be proved. So fixed T dispersion relations now can be proved starting from the Lehmann-Simanzik-Zimmermann representation. Now let's go to partial wave analysis. The amplitude is a function of the scattering angle, and you simply expand it in Legendre polynomials. BSc exercise. L has the physical significance of angular momentum, and those are the Legendre polynomials. This series converges for real angles, but now we have gone to complex angles, and you have to be very careful. The Legendre polynomial for complex angles has this kind of a term, and you see that because of non-zero imaginary part to the angle, there is an exponential growth in angular momentum, which means this series will not converge unless the scattering amplitude has an exponential decay for large angular momentum. And this is what Lehmann showed, that ALFS actually has an exponential dependence, and gamma is essentially related to theta I. And this is in fact another way of understanding the Lehmann ellipse. Now, complex angular momenta took only integer values. We are making everything complex. Can I make angular momentum also complex? Okay? In particular, can a function ALFS be found for complex L so that when L is integer, it agrees with the scattering amplitude? And if you could do it, is the continuation unique? The answer is no. This is again some highbrow analysis in complex variables. There is something called the Carlson's theorem, which says unless the ALFS has an exponential fall off for rather general values of lambda, and the Lehmann ellipse does give you such an exponential fall off, therefore you can indeed continue to complex angular momentum, but not all values of real L, but real L has to be larger than a certain L. Then you can indeed find an ALFS which is holomorphic. That means it's an analytic function of the complex angular momentum. Now, can you always guarantee this? No. There are two circumstances where this can be proved. One is potential scattering, which was done by Reggie. The other one is if the amplitude satisfies dispersion relations with finite number of subtractions. What does subtraction mean? If you go back to our first result here, there is no guarantee that the functions are such that this integral will exist at the upper limit, and then you do what is called subtraction. You subtract a value of this at some fixed point and then rearrange things in such a way that the omega prime integration does converge, but the price you have to pay is an unknown function. Okay? So that is what we mean by subtraction. Yeah. So as long as you have dispersion relations with finite number of subtractions, this is guaranteed, and that number L here is related to the number of such subtractions. So you see, dispersion relations are again coming back in a very, very important way to decide whether analytic continuations are possible or not. Now we go to something called the Sommerfeld-Watson transform. If A of S is holomorphic, then that series can be converted into an integral. Unfortunately, I couldn't figure out how to draw diagrams, so I pulled this out of wiki. This diagram is wrong because according to what I said, only for L greater than a certain value do you have holomorphism. So you have to shift this contour to the right. This is a naive implementation where capital L is taken to be 0, and there is no guarantee of that even in relativistic quantum field. So I'm using this figure, but I'm warning you. So what do you have to do now? You split the partial wave amplitude into two parts, one where L is smaller than capital L, other one where larger than capital L. For larger than capital L, you use the Sommerfeld-Watson transform, and for the other part, just leave it as a series. Okay? And now, please give me a little bit more time. You know, the magic about contour integration is you can stretch it whichever way you want. Okay? You know, would put even a yoga expert to shame what you can do with contours in complex variable theory. So what I'm going to do now is that contour, I'm going to stretch it out so that it runs along the imaginary angular momentum axis at real value equal to capital L. Okay? I can do that because A LFS is holomorphic in that region, and as I stretch the contour, I don't pick up any extra contributions, and that can be done. And this gives a new representation to that integral, which is of this form. In the naive way of doing it, which I don't know whether you can read or not, there is a sin pi L in the denominator. Its only role was to reproduce the integer values, because sin pi j vanishes for j integer. It's a simple pole. Pick up the residues and you reproduce the standard partial wave expansion. That is why you introduced it, but now a miracle has happened. And that is that since capital, the real part of L is fixed, the imaginary part of the angle plays no role, and it converges for all values of complex theta, all values of the imaginary part of the angle, much beyond the Lehmann ellipse. What is more, sin pi L now behaves like e to the is exponentially grows for large L, so this integral becomes super convergent. Okay? So that is the beauty of this representation, and now we come to what I call the miraculous regipole. That Tullio Reggi, by the way, even though I'm talking about his contribution in terms of regipoles, he was a genius. He made all kinds of contributions to doing non-perturbative quantum gravity calculations, computer science, etc., etc. So now what we want to do is, what have I done? Is there a little bit of chalk here? Okay, don't worry. So no, leave it. It's not necessary. I'll just do my hand waving. Good for exercise. Okay. So there is a line at capital L. To the right of it, I have holomorphic continued partial wave amplitude. Can I try to move it to the left? Three things can happen. The amplitudes continue to be holomorphic, then you pick up no contribution. They can pick up some poles. In other words, they can become meromorphic. That can be handled. They can get all kinds of crazy complex plane singularities like cuts and colliding cuts and what have you. Can't do anything. You just have to quit. Okay? So these poles are called regipoles because Regge discovered them in potential scattering. So typically, the regipole will look like a pole in the complex angular momentum plane. This is the trajectory function, that is the residue function. So what? Suppose you have a trajectory such that the real part at some S0 becomes an integer. Then when you expand around it, this is what the form of the amplitude is, but lo and behold, it's okay. This is a pole at S equal to S0 with an imaginary part, and it is nothing but what we call a resonance in particle physics. So regipole can give a natural explanation for resonances. That's one thing. But now, there is another aspect of it. Since there is a pole here, you pick up a residue from that. This is at some L equal to alpha, and that residue will give me a Legendre polynomial, not at integer L, but at some alpha S. And what is the significance of that? And when you take large T, this behaves like T to the alpha S, which means in the T channel, the high energy behavior is also governed by the same regipole. So regipole, even though it was introduced as a complex plane singularity, brought a conceptual simplification of bringing resonances and high energy behavior of scattering amplitudes into one fold. Now that is a very important lesson. If you look at a typical experimenter's data, say pipeless proton scattering, at lower energies you will see all these bumps. It's as if the particles are resonating with each other, and at high energies it reaches a smooth behavior. And now what regipoles are saying is that these can be due to direct channel regipoles, and this could be due to cross channel regipoles. So the scattering amplitude, one end you describe it to regipoles of the cross channel, and this end to the regipole of direct channel. So what? And next comes the surprise that suppose there is an amplitude such that this imaginary part falls faster than nu inverse, which means both A and nu A satisfy unsubtracted dispersion relations of this form. You just multiply this by nu, subtract each other, and you get a relationship like this, and this is called super convergence relation. Just dispersion relations were used to derive that and nothing else. So once more, the dispersion relations are coming and doing something, but this means what does this mean? The low energy part of that graph and the high energy part are related, which means direct channel regipoles and cross channel regipoles are related. They are not independent. The correct way to say is that they are dual of each other. It's like wave-particle duality in quantum mechanics. You can either use a wave description or a particle description. They are dual to each other. They are not two different aspects which you put together. One consistently done should take care of the other. So here, either you do regipoles in the direct channel or you do them in the cross channel, they should give the same result. And this was a big shock to those trained in field theory. It says, for example, this is the direct channel regipoles, cross channel regipoles. You don't add them because they are the same. If you add them, you double count. So these are called duality amplitudes, and this is completely different from QFT. If you do electron-positron scattering in QFT, this is the direct channel exchange, and this is the T channel exchange, and you must add them. And you must add them with the right sign, otherwise you get wrong. Now in strong interactions, you either take one or the other and don't add them. Duality. That's how duality was born, and this immediately led to string theory. Since I'm running out of time, I'll very quickly tell you what happens. There were three creators of string theory, Yoichiro Nambu, and this is my close friend Holga. He even visited Chennai many years ago. Some of you might remember, And he said, but I don't see any elephants on the road. And I told Holga, please, you shouldn't have such stereotyped images of India. Elephants don't walk on our streets. And just then we heard some jingle bells. I was living in Indiranagar. There was an elephant walking on the road. That turned out to be an elephant of some wedding party that was going on. So that shows that you can never be sure of anything, not even of your own country. And the third one is Susskind. These three independently discovered. One missing link I didn't mention was that Veneziano wrote down an amplitude which explicitly showed this duality, exact duality. And then that Veneziano amplitude was generalized, and when they generalized it, these three gentlemen in different ways saw a string, okay? Now that is really remarkable, and so this is string theory for you, that what a diagram like this in string theory would look like this, and this would look like that, and there is no difference between them, okay? They are one and the same. So the theory that realizes duality is string theory. I've said it in words, but an action was written down, and that action was quantized and all that. So now I'll come to my end. I'll just end with an epilogue, okay? That string theory soon was discarded because it led to various unphysical features for strong interactions. I don't have the time to go into all that. And this was replaced by a relativistic quantum field theory. So field theory came back. I think Star Wars should be redone in terms of field theory and string theory, and instead of Return of Jedi, you have Return of Field Theory, like that, At least maybe our physics students will get entertained by it, because I can't imagine, a philosophy student getting too excited by this way of looking at things. And there are many experts in our institute on quantum chromodynamics, both the perturbative aspect and non-perturbative aspect. Non-perturbative also, there is the Lehmann-Simanzik type, then there is the lattice type. One is LSD, the other one is lattice, okay? I mean, when some people get high on lattice more than on LSD, so that's fine. So, but this field theory also had a problem because quarks were never seen. And this was an embarrassment which was converted into a virtue by saying quarks are confined. But your theory must produce a mechanism for that, and that mechanism was proposed by Mandelstam, Tooft, and Polyakov. According to this, if you take, for example, a plus charge and a minus charge in electrodynamics, the field lines go everywhere. But in QCD, if you take a quark and an antiquark, the dynamics squeezes the flux into a thin tube between them, and then flux conservation makes it that you have to spend energy proportional to the distance of separation, and that's why we don't see them, because to separate them, you have to give lots of energy. Okay? And narrow flux tubes permanently confined quarks. And there's a long story about it in lattice gauge theory, how these flux tubes have been established without a shadow of doubt. In 2004, I built this Kabru supercomputer, which is very kindly referred to. And at that time, 2 years before, there was a revolutionary algorithm by Lusher and Weiss, and Pushan Majumdar had learned all about it. And Pushan and myself, we put this Kabru to full use, and we were able to show that these flux tubes, they could be studied so accurately that they actually behave like the fundamental bosonic string, which we had thrown it away. So that's why the title of my book is Strings. Started with strings, threw them away, and we have come back to strings. Last point. Mandelstam, when he began this whole exercise, proposed a very beautiful representation for scattering amplitudes called the double spectral representation. This could not be proved after a lot of effort. Mandelstam himself put a lot of effort. To this day, it remains unproven, and it's a challenge for physicists and mathematicians to join hands and prove this Mandelstam double spectral form. And I just would like to show you a picture of Kabru that I had built in 2004. As I already mentioned, it reached a performance of 1 teraflop, and only a very small number of people were involved in building it. Sanjay, Hemant, Amal, Shyam, Ishwar. And twice in a row it was in the top 500 supercomputers of the world. And I named it after Kabru because it's one of the most spectacularly beautiful peaks on the border of Sikkim and Nepal. And my motivation was that this computer, if you look at the Himalayan hierarchy, Kabru is not the topmost mountain, it's somewhere. So the message was that, okay, we have done a good job, but we still have to go till we build an Everest in this institute. And I didn't do it, but I'm sure somebody else will do it. And thank you for your patience.
So, okay, thanks Professor Haridas for this fascinating talk.